This is 2.1.4. Particle interactions. Now, just a recap, and we're going to capture what we've talked about in the last few lessons, is that there are 4 fundamental forces in nature. And these 4 fundamental forces, we're now going to put them in order of their strength. So number 1 is a strong nuclear force. Then we've got the electromagnetic force. Then the weak nuclear force. And then finally, gravity. So 4 fundamental forces. Strong nuclear force. Then electromagnetic force. Then weak nuclear force. And then finally gravity, or gravitational force, if we want to stick to the convention we've just done. And then I'll do an arrow pointing downwards, which is strongest to weakest. Next, we're going to start with exchange particles. And in particle physics, the exchange particles describe how different particles interact with each other, or how they apply forces onto each other. So this might come across as quite strange to you guys, because it's the first time you're seeing it, but I'm going to try to explain it in a way that's simple. So exchange particles mediate forces and we'll be using them for electromagnetic attraction and repulsion, and we'll also be using them for beta plus and beta minus decay. And we'll also be using it for a process called electron capture. So they mediate forces between particles. And it's used for electromagnetic attraction or repulsion. Also used for beta minus and beta plus decay and electron capture. So let's look at how it works. First, let's imagine we have 2 electrons near each other. So imagine 2 stationary electrons near each other. You would normally just say that they're both charged, so therefore they apply a force on each other, and that's it. That's how you would describe it. But in particle physics, the description is a bit more than that. So in particle physics, something has to carry the force to the other particle. They don't wirelessly communicate the way that you typically think. So what happens is, one electron emits a virtual photon to the other electron. So if this is step 1, then in step 2, this electron has just emitted a photon towards our second electron. Now, I mentioned in one of the lessons that photons are massless, but they carry momentum. So if that electron, which was stationary in the beginning, has now emitted a photon, now there is some momentum, and momentum is always conserved. So that means there must be a backward momentum, a recoil, in that electron to conserve that momentum. So that first electron moves backwards. So this is the virtual photon. Now, that virtual photon with its momentum is absorbed by our second electron, and that virtual photon had a momentum towards the right, so that electron now moves towards the right. So second electron absorbs virtual photon and gains its momentum. So step 3, this electron goes that way, and this electron goes that way. So these exchange particles that we're about to talk about, I've only talked about one so far, which is called the virtual photon. And we'll talk about more in a minute about the others. But we call these gauge bosons. So gauge boson is the proper name for exchange particles. For? Well, electrons are negatively charged, but if there was 2 positrons or 2 protons, same thing would happen. Yeah? If they repel electromagnetically, then the repulsion is done by shooting or by emitting a virtual photon. And the virtual photon carries that force. The interaction happens because something carried that over. In this case, no, one emits to the other. One electron emits the photon, one absorbs the photon. Now we'll construct a table. So we'll write interaction. We'll do the gauge boson and the particles that it affects. So we'll start with the electromagnetic. And this is for both attraction or repulsion. The gauge boson is the virtual photon. Which has symbol gamma, lowercase gamma. And the particles affected are charged particles. So anything that has a charge. So, for example, protons, electrons, muons, tau, plus their antiparticles. Next is the weak interaction. So the weak interaction is responsible for beta minus and beta plus decay, or electron capture. And for that we use the W minus, the W plus, or the Z naught bosons. So these are also charge carriers in a way. They carry charge away from something and then they decay later on. And we'll look at that more in a moment. So these affect things that are usually in a nucleus. So protons and neutrons. So you have a weak interaction, and the weak interaction is responsible for beta minus plus decay, and also another process called electron capture, which we're going to look at in a moment. And the exchange particles that relate to the weak interaction are called the W minus, the W plus, and the Z naught bosons.
What is it?
Those are the exchange particles that relate to the weak interaction. So they're responsible. Bosons are the exchange particles. So the virtual photon, the W minus, the W plus, and the Z naught are bosons. They mediate these forces. So we say an interaction, what force is it using? Electromagnetic or weak? So what particle is responsible for making that happen? The virtual photon makes it happen. So two things are repelling, the virtual photon is involved between them. If they're attracting, the virtual photons are still involved. If it's weak interaction, so beta minus or plus decay, it's one of those W minus or W plus that's causing it to happen. And when we start drawing Feynman diagrams on the next page, it's going to start to make sense as to how these actually work.
You know, on the previous part it said one electron emits a virtual
Yep.
proton. How comes the other one doesn't as well?
Well, the other one could. It's one or the other.
It's only one or the other. They can't
One or the other. Well, if one emits that photon, by emitting the photon, it itself has already gone backwards. And then when that photon's absorbed by the other electron, that electron then goes the other way. So repulsion has happened.
Isn't it possible for both of them to just emit photon?
If both of them emit a photon, then when the first one's emitted a photon, it's going to recoil backwards. When the second one's emitted a photon, that's going to recoil backwards. But then when they absorb each other's photons,
Where do they collide?
They're gonna go backwards.
then they're going to go backwards even more. So it's not going to work.
If they both go towards each other emitting photons, why don't they just...
No,
photons
the
that do
the
that?
photon is exchanged at the point at which they interact with each other. The photon causes the force. Without the photon, they don't wirelessly force each other. So particle physics describes forces as being carried by something else and then given to something else, rather than two things existing with a separation between them just experiencing the force.
So what tells the electron to emit a photon? Like, why does it do it?
Because they're charged and they experience the electromagnetic force.
So, they're like,
So when they experience the electromagnetic force, in particle physics it's described as one electron emitting a virtual photon, which causes it to recoil, and then when the other electron absorbs it, that electron gains momentum in that direction, and they move away from each other, so they have repelled. So a force has been exchanged.
is it like...
Yes.
For the thing, particles for weak interaction, the electron capture should be electron.
We haven't looked at electron capture yet, but I'm going to show you that. Yeah? We're going to look at that on the next page. So let's start a new page. And we show these interactions using Feynman diagrams. Now, Feynman diagrams are time diagrams. And they show how particles change or interact with time. So let's do an example of that. Let's do electromagnetic repulsion. So I'm going to label that as time. At the bottom we've got the before, and at the top we've got the after. So I'm going to draw the same electromagnetic repulsion I did as a 3-step diagram in a Feynman diagram, which will show everything happening. So, in a Feynman diagram, we start with having 2 electrons, and say our 2 electrons are moving closer together as time moves forward. So as we go up, time is moving forward. So everything's always going to point upwards. So as time moves forward, the electrons are getting closer together, then they interact with each other. And when they interact with each other, they repel. So, the moment they repel, these electrons then move away from each other. So you just follow from the bottom and you walk your way up to the top. Now, I said that the force was mediated by a gauge boson called the virtual photon. Now, the virtual photon almost instantaneously goes between those electrons. So the gauge bosons are drawn as a squiggly line, and then we just label that with the virtual photon gamma. So now when we describe it, we start at the bottom, we've got 2 electrons coming close to each other, then there's an exchange particle between them, and they move away from each other. So that's the description of a Feynman diagram. No, this is a virtual photon, that's it. That's what it's called a virtual photon. The gauge boson is represented by a squiggly line. The particles are represented by solid lines. Yes?
What's that line that comes up in the middle?
The squiggly line is the gauge boson.
Yeah, I know, but in the middle of that squiggly line, there's another one.
That's a gamma, the symbol, lowercase gamma.
Oh, I see.
So virtual photon has the symbol of lowercase gamma. Greek letter. Yeah? The ones from the week had W's and Z. That was a lowercase gamma. Now let's write what this is as an equation. So in the beginning, you've got an electron plus an electron. And afterwards, you've got an electron plus an electron. That's repulsion. You start with 2 electrons, you end up with 2 electrons. Right, I'm going to quickly do the rest of them and then we can ask questions later. So next, we've got beta decay. Now for these ones, I'm not going to draw the time axis. We're just going to assume that they're there. So in beta decay, we start with a neutron, who then changes into a proton. At the moment when the neutron turns into a proton, it decays via the weak interaction. Now for a neutron to become a proton, it loses negativity. So if we remove negative charge from a neutron, it becomes a proton. So neutron minus a negative charge becomes a proton. So then we have W minus, which comes out of the neutron at the point where it decays, which is the vertex. The W minus moves away from that event, slightly. And then the W minus itself decays into two particles, which is the beta minus particle and the electron type antineutrino. Now, I have drawn the antiparticle arrow as going backwards. The particle itself is not actually going backwards, just by convention we draw them as going backwards. So the backward arrow just says it's an antiparticle, but it's still going up. Yeah, because time goes that way. We'll save questions for later. So this is beta minus. And the equation for that is a neutron becomes a proton plus a beta minus plus an electron type antineutrino. Next I'll do beta plus. So beta plus, we've got proton, turns into a neutron. Then the W plus, it loses positive charge, so W plus this time. Now we've got an electron type neutrino, not antineutrino, and a beta plus. Now, in this case, you can see that the gauge boson is slanted. And it's slanted because it doesn't decay immediately, it evolves in time. So it takes some time for it to move away, and then it decays. Now I'll do the equation for this as well. So we've got proton turns into a neutron plus beta plus plus an electron type neutrino. And then lastly, we're going to do electron capture. And then we'll end the lesson. So with an electron capture, in the beginning we've got a proton and we've got an electron. The electron gets too close to the proton. The proton then eats that electron. So W minus is carried, the electron charge, the negative charge, towards the proton. The proton then turns into a neutron, and the electron has lost its negative charge. It becomes a neutrino, an electron type neutrino. And that is the end of 2.1.4.